All right, so let's start with the following problem. So again, randomly arrange the word letter. All right. What is the probability that the arrangement contains EE or TT? So EE or TT. Okay. This is similar to the problem asked earlier, right? You have what is the probability? What are the all the possibilities where you have big EIG pattern or you have out pattern? Okay. So let's have the following. Let's call this event E. So let E be the event that EE appears together. Yeah, appears in the arrangement or rearrangement, whatever you want to call it. And let T, I'm just using the same name so that it's easier. So T be the event what that basically that TT appears. Okay. So now, so let's see. So let's try to see basically what is the size of E. So what you want is you want EE to be together, isn't it? So how can we have EE together? Note that we can say let's call EE to be something which is not here. Let's call EE to be X, right? Now, what are all the permutations of EE then? Like, what are the all permutations we're looking for? We're looking for EE is, let me just explain EE now. So EE is basically, we are looking at all arrangements of L, T, E, R, S, and X. Isn't it? Yeah. So that is all the E, all the, what do you say? All the, it's basically the event E, right? So we need to count the size of event E. The size of event E is the arrangement, and recall with the repetition of the arrangement, it is going to be what? You count the total size. So 1, 2, 3, 4, 5, 6. 6 factorial divided by how many of them are repeating. The ones which are repeating is basically TT is repeating, so divided by 2 factorial. So that is my size of E. Is that okay? Now, similarly, what is the size of T? Same, right? Because, well, if you look at this, there are 2 T's as well, right? So it's going to be what? Again, so it's all arrangement of, let me just write down, explain T a bit. So T is rearrangement of L. So let's call TT to be, say, Y. Then we have what? Rearrangement of L. Uh, then we have E, Y, E, R, S. So that's going to be, again, 6 factorial divided by 2 factorial. All right. Now, generally, we care about the sample space in advance. All right. So let's see what is the size of the sample space. The size of the sample space is, you're looking at all the arrangement of what? How many letters are there? 1, 2, 3, 4, 5, 6, 7 letters, right? So it's an arrangement of all the 7 letters, but 2 of them are repeating twice, right? So E is repeating, that is 1 repetition of alphabet E, and then TT is repeating. So it's going to be what? It's going to be 7 factorial divided by 2 factorial for E and 2 factorial for E. So this is the size of the sample space. All right. Now, let's go back to the question. The question is saying, what is the probability of arrangement containing EE or TT? Or is always union, right? Make sense? So we are looking at probability of, so let's say we are looking for probability of E union T, isn't it? That is same as size of E union T divided by size of the sample space. Okay. All right. Now, we have already figured out what is my size of E. The size of E union T is size of E, which we figured out, plus size of T, which we also figured out, minus size of E intersection T. So we need to figure out what is E intersection T. Yeah. So let's go back and do what we did earlier. So intersection T, we can call EE to be X and TT to be Y, right? So in E intersection T is rearrangement of what? It's a rearrangement of L. Instead of E, we have X. EE is X. Then we have what? Y. We have E. We have say Y. Then instead of TT, we have Y. That's what we have. Then we have what? R and then S. So it's a rearrangement of 5 letters, which is going to be what? 5 factorial, isn't it? So this size is going to be, so this value is 5 factorial. So let's write down what is E union T. Size of E union T is going to be 6 factorial divided by 2 factorial plus 6 factorial divided by 2 factorial minus 5 factorial. Okay. That you can simplify it a bit if you want. So this is going to be 6 factorial divided by 2 plus 6 factorial divided by 2. So that is going to be 6 factorial minus 5 factorial. So what is my probability of E union T? Is going to be 6 factorial minus 5 factorial divided by this number, size of the sample space, which is 7 factorial divided by 2 factorial. Okay. And the main fraction line should be clear. The main fraction line is here. So we have so this is my probability of E union T, that we have either E. This is similar to your counting in the quiz as well. You had dig and you have out, right? So dig pattern was what? So you could have dig as X and out as Y, right? So how many ways can you get dig? So it's going to be dig is 1, so let's call it X. That remaining 23. So it's a 24 what? It's going to be 24 factorial there. Similarly for out, you have what? Another 24 factorial. Now, then you talk about the intersection. The intersection is going to be what? Dig you call X, out you call Y. Now, there's 6 of them are exhausted in X and Y, and then there is 20 more. So 22 factorial. All right. So this is how you could have worked out that problem. Okay. But then that again has nothing to do with probability. That is about counting, really, right? So here you can see probability. The only extra thing is we are dividing by the size of the sample space, and that's what leads to probability. But all these are essentially counting problems in disguise. Does that make sense to you? Okay. All right. Okay. So next thing is we want to talk about conditional probability. Okay. So let me basically write down a problem, and that will basically motivate us. So here's a problem. So problem exercise 539 is the following. Suppose we flip or flip coin 3 times. Okay. What is the probability of getting odd number of tails? Given that the first throw is tail, given that the first throw or the outcome of the first throw. So let's see. So we want to here, let's try to understand this event, okay? So what we have is the following. So we are flipping coin 3 times, okay? Now, when you flip a coin, there'll be head, there'll be tails, right? We are counting the probability that what? There's odd number of tails, right? But you're already given that something has happened already. What has happened? That the first one is what? tail, right? So let's try to understand this problem. So let's see what are the chances. So first one is always tail. That is given to you, right? The first option is tail, right? And I'm reason why I'm writing four of them because first one is tail. I have two possibilities for the second one and two possibilities for the third one. Okay. So now, so I have tails. The first one is tail. That is known to me. Okay. Then the second one is what? Then we have second one could be what? Head or tail. So head, head. Then I have tail, head, and tail. Okay. So what is the probability of getting tails given that what the first row is head? The first row is head is this one. And now which one of these have odd number of tails in total? This one has odd number of tails in total. And what about this one? This one has odd number of tails in total. All right. So we have what? 2 over 4, which is what? 1 by 2. Does that make sense to you? So the probability of this happening is actually 1 over 2, not 2 over 8. Yeah. Because generally what happens in probability is that you have all the possible outcomes and then your event has some outcome. And then you divide all the possible, sorry, you divide the size of event by all the possible outcomes. Does that make sense? Now here, all the possible outcomes are already what? Are restricted because you're saying given that the first one is tail, right? Does that make sense to you? Yeah. So the first, so you're basically considering a part of a smaller event. Okay. So let's try to make the sense of it. So suppose we want to know, suppose this is the idea behind conditional probability. Okay. So suppose we want to know that probability of event. So what is the idea? Probability of event. We want to know. Suppose we want to know probability of event A, given that B has already happened. Okay. Is that okay? All right. So you're basically that given we know that B has already happened. All right. Yeah. So in that case, we call this as, so if A depends on B, yeah, we call this as conditional probability. And this is how the definition is, and then we'll try to make a connection with this example. Let's see. So let the definition of conditional probability. So we have what? Let A and B be two events. Okay. Then the conditional probability of A given B is equal to, so the notation for that is you write it like that. So you say P, you read this as probability of A given B has already happened. Or you say read this as probability of A given B. Yeah. This is going to be probability of A intersection B divided by probability of B. Is that okay? So probability of A given B, that B has happened already. And then you're asking what is the probability of A happening? That is given by A intersection B divided by probability of B. Okay. Now here, of course, one should demand, and that's why I waited for it. One should demand the probability of B should be what? You write PR, you can write P as well. Okay. Yeah. So what is the probability of B should be what? Greater than 0, right? Because we are dividing by probability of B. The probability of B should be 0. Okay. So this is the conditional probability. So again, what is the conditional probability? That you are looking at what? You're looking at the event where what? A has already, so in this case, B has already happened, and then you're looking for what happens with B. What is the probability of A happening? Yeah. It makes sense, right? Like you're thinking about something like this, right? So you say, okay, just let me give a random example about exam. Yeah. Let's say, just say, suppose passing and failing in exam is random. Just think about it, okay? That's random. So now you have basically the question, what is the probability of failing in all three exams? That is different than what is the probability of, you already know that you have failed the first exam, and what is the probability of failing the other two exams, right? Because one is certain now. There's no other option for the first one. Does it make sense to you? So here, what your your B is certain, B is done, right? So so you are finding what is the probability of A given that probability of B. So in this case, for example, what will be my B? So I'm looking at B. So B is something which has already happened. So what has already happened given that the first one is what? Fail. That is B. Yeah. And then we are asking what is the probability of what? Getting a odd number of tails. This is what? A. Okay. So this idea is basically the idea behind conditional probability. Does it make sense to you? Another way to think about this problem is the following. You can think about it as now your new sample space is B because B has already happened and you're looking at part of B, which may happen, may not happen. Okay. So the idea is you have event A, you have event B. Yeah. B has already happened now, right? So B has happened. That means what has happened? This part has already happened. Yeah. So now what is the possibility of A also happening at this on top of B? Yeah, that is gonna be this part here. Sorry, let me use a different color pen. Let's draw this again so that makes sense. Let's look at this again. So we have the following. So we have, let this be set A, and then let's take another one. Okay. So suppose I have set A and set B. So I have A, I have B. So now B has already happened, all right? So now, so B has happened. That means my B is the one with the certainty. So I'm in the case where B is my now sample space because everything in B has happened. Yeah. So B is my new sample space. Does it make sense to you? Yeah. So I'm going to basically look at the size of B because that is my new sample space because that is all the possible outcome. Yeah. And then I'm asking what is the probability of A happening given that B has happened. So now what part of A can happen? What part of A can happen is the only this part. Do you agree? Yeah. Because outside that, that is not even part of your sample space anymore. Because when you say conditional probability, you are restricting your sample space because your sample space is now all the possible outcome is all the events in the B. Everything in B has happened. And that is now your new sample space. Okay. So then this should be what? Size of what? A intersection B. So probability of A given B is size of A intersection B divided by size of. Okay. And now you can do a little bit of repolishing to make it connect with the old probability. So this is going to be divide top and bottom by size of S. So the top becomes what? Probability of, we should fix a notation. Maybe I will use a small p notation because I don't want to write PR all the time. Save on some space. So it's going to be probability of A intersection B divided by what probability? Does this make sense to you? Anyone? Yeah. So this is the idea behind conditional probability. Conditional probability is probability of A happening given that B has already happened. Yeah. Okay. Now let's look at the next problem now. So here we go. So here we are. Let's see the following. Another problem. So what is the probability that a bit string of length 4 contains at least two consecutive zeros, given the first bit is 0. First bit is 0. So here, see, the idea is again about conditional probability because your 4-bit string, and the first one is given to you 0. What is the probability that you will have two consecutive zeros? Does that make sense to you? Yeah. Can you think about this problem now? There are two ways to look at this problem. All right. One way is basically you either only consider B, yeah, as a sample space. What is my B? Let's label everything. Okay. So let's have A, B, C. So B be the event, B be the event that first bit is 0. Okay. Let B be the event that the first bit is 0. And now you're looking at what? You're looking at out of those, how many of them have consecutive zeros? So that's one way of looking at this problem. All right. Another way of looking at this problem is by basically conditional probability, which is P of A intersection B upon P of B. So let's talk about it. So B, in this case, we have to compute probability of B. So we need to know the whole sample space. So let's look at the whole sample space. Whole sample space is all the 4 bits, right? So what are all the possibilities for the 4 bits? 2 to the power 4, right? There are 2 spots. Each one of them have zeros and ones, right? Now, what is the probability of B happening? So P of B is, well, first one is fixed. It is 0. So now there is the only possibility of the 3 bits, right? So the first one is fixed to be 0. And then there are these 3 possibilities for this guy. So 2 times 2 times 2, isn't it? So probability of so let's talk about the size of event B first. The size of event B is going to be 2 to the power 3. Do you agree? Yeah. Now you want to talk about A intersection B. So A is basically that we have what? Consecutive zeros, right? How many? 2 consecutive zeros, right? So A is the event of at least 2 consecutive zeros. At least 2 consecutive zeros, right? Yeah. Now what is A intersection B? Let's list it out because we have a small set. We don't have to basically, yeah. So A intersection B is what? The first bit is definitely 0, right? And now you're checking what are the other possibilities. So 0, you have 0. Let's just write it down. So 0, now we can have what? The first bit can be either 0 or 1. that okay? Then for this one, we have what? Either the next one is 0 or 1, right? And then we can have either 0 or 1. Here we can have either 0 or 1. Okay, so this is all possible, right? We agree? Because they all have what? 2 bits in common. Sorry, 2 consecutive zeros. Now let's look at the next branch. I had 1. This is my second bit. Now what about the third bit? Third bit can be either 0 or 1. Yeah. Now fourth bit. So first bit, second bit, third bit is and fourth bit is either 0 or 1. So this is not a possibility, right? Do you agree? This is not a possibility because I need 2 consecutive ones, right? Then here I will have what? I have 0, 1. Well, then there's nothing here which will basically give me any option. So my A intersection B is what? I have 0, 0, 0, 0. I have 0, 0, 0, 1. I have 0, 0, 1, 0. I have 0, 0, 1, 1. This is for this branch here. And then the other option is what? 0, 1, 0, 0. And that's about it, right? There is no other option really. Do you agree with that? So this is my intersection B. Note there are other ways to count it too. You can count it in different ways, but let's say this is the A intersection B. So what is my size of A intersection B? Let's see. So what is size of A intersection B? It's going to be 1, 2, 3, 4, 5. Size of A intersection B is 5. Yeah. So what is probability of A intersection B? Is going to be what? 5 divided by 2 to the power 4, right? And then similarly, what is the probability of B? Is 2 to the power 3 divided by 2 to the power 4. Do you agree? Yeah. So therefore, what do I get? Therefore, probability of A given B is 5 divided by 2 to the 4 divided by 2 to the power 3 divided by 2 to the 4. 2 to the 4 to the 4 can cancel. So the answer is 5 over 8. Does this make sense? So what is a random variable? Right. Okay, so let me basically talk about it. So randomly. So in some sense, you can think about the easiest way to think about random variable is it's an assignment. A random variable is an assignment of set to a real number. So this is a very vague definition. We'll make it precise in a moment. All right. So you can think about it basically as a function from set S to set of real numbers. Okay. So that gives you a random variable. But you're not interested in any set. You know, where does it comes the problem? Where the probability theory comes into the picture? You are basically talking about random variable of a set. That means it's a set of events, right? And a set basically is a set of is an event set. Does it make sense to you? Okay. So let's look at an example. So suppose you toss a coin. Suppose we toss a coin. Example. So suppose a coin is suppose a coin is is tossed or flipped 3 times. So you flip a coin 3 times. Yeah, with outcome edge. With the outcome being basically what? Say outcome be T. Okay, T is the outcome. All right. Yeah. For example, if I flip, so for example, one outcome of T could be H H H. For example, yeah. Yeah. You have basically 8 possible 2 times 2 times 2, right? All the possible outcomes. Right? So now where? Okay. So this is a. So now where is the random variable coming to the picture? So let X of T denote be the total number of what? Total number of heads observed. Okay. So let's try to basically make this picture clearer. So now let's see. So let's associate now the random variable. All right. So let's see. So in this case, so what is the definition? The definition is the total number of head observed. So let's see. If I toss a coin 3 times, the possibility is that I get H H H. We agree. My T is H H H. Yeah. In that case, what is the value of this function? Total number of head observed. What is the total number of head observed here is what? 3. So the output of this function is what? 3. So this is my random variable as a function. Make sense? What will be X of H? So let's say X T H and X of say H H T. Again, in this case, it will be what? How many heads are here? 2. Here also there are 2, right? Or the same thing is for, I can write this as, this is same value for X T H H, right? So essentially it's just a function, all right? It's a function from set of outcomes to real numbers. Yeah. Again, what value it could be, that's another story. But we can define something like half of the number of heads as well. So first will be then in that case 3/2, second will be 1, third one will be 1. Yeah. So you can define it any function to the real numbers, right? I mean, which of those are interesting for us? That's another story. I mean, we don't define arbitrarily numbers, but for example, random variable where we want to know the number of heads is an interesting one. Okay. So similarly, we can have X of what? TTT is going to be what? In that sense, it's going to be. Does the random variable make sense? Let's just look at a few more examples. So what is X of TTH? Or the same as X of HTT, which is X of what? H. So HTT, and then we have THT. These are all values, right? Do you agree with that? So this is basically what are random. Okay, makes sense? Yeah. Now let's look at another one. Now, suppose another example. So suppose a pair of so example again. We'll soon see why do we care about these, huh? Yeah. So example. So a pair of dice is rolled. Yeah. Okay. So let Xij be basically the total what? Total of numbers. I mean, dice, I mean, like we are assuming standard definition of dice. So we have what? 1, 2, 3, 4, 5, 6. Okay. Right? That is the what outcome of one of the dice, right? So both the dices have outcome coming from one. Okay. So now, what is, so let xi be the total of the numbers rolled. Okay. So in that case, what do we get? We get what? We have x of 1 is going to be what? Simply what? 2. Yeah. And again, this is one example of random variable. You could have many examples of random variable. You could have a constant random variable. No matter what, the output is 1. I mean, what does it capture? That's another story. Is it going to capture some interesting phenomena? Maybe, maybe not. Right? Does it make sense to you? You could have a random variable which will basically say a random variable where the output is 1 if all of them are head, otherwise it's 0. That's also a random variable, right? So random variable is the arbitrary, like, any assignment of the outcomes, right, which is a set, right, or in elements of the set to the numbers is a random variable. All right. Some of them turn out to be interesting, some of them are not. It's like functions, right? Functions are also like that. Some functions turn out to be interesting, which you say, example in calculus. So, you talk about sine x and cosine x and their derivative, but you could have crazier functions which we don't care about. Make sense? Just 1 second. Yeah. Yeah, what we have x of 1 is going to be what? X of 1 is 1, right? We have x of 1 is going to be what? Is 3, right? Or we have x of ij is going to be what? I plus. Is that okay? Yeah. Now, so this is the idea here. All right. So now let's ask the following question. All right. The question: how many ones can I expect? Can we expect in a bit string of what? In a bit string of length. Okay. Now, so how many can we expect in the bit string of length 100? Think about this problem. So now when you look at the bit string of this problem, it's slightly simple. You can say, oh, 50, right? You agree? Yeah. Because you'll say, okay, uh, uh, generally we expect that half of them to be what? If I randomly choose one, then will be half of them will be 50, half of them will not be 50, right? If I change the fraction, say I say a probability of 1 coming is say 1/4 and probability of 0 coming is 3/4, then what do I get? Yeah. Or if I have 3 different options, say I have 0, 1, star, then what is the probability of getting, what is the expected value of number of ones? Okay. So this is the question. So how many ones can we expect in a string length of 1? Okay. So what is the expected value of what? The number of ones in a bit string of length 100. Okay. So let's make this precise. All right. So here is the thing. So we have definition. So the expected value of a random variable x. Yeah, I want to just make sure the input of this function is s as well, just to make it clear. So expected value of a random variable x, s, on a sample set s is given by e of capital X is equal to summation. It has to do with the, do you agree that this has to do with the probability of something coming up, right? Do you agree? Yeah. I mean, look at the other one. How many ones can we expect in the bit string of length 100? Now this depends on how many times one can happen, right? If I roll the, if I flip the coin, for example, because bit flip can be thought of as a coin if you want. So now, so this is going to be probability of s happening, xs, and you're summing or over all s in s. this is the expected value of what? Of a random variable over a sample space S. Is basically, first of all, what is the probability of S over XS? Okay, so let's basically let's think about this problem now. Okay? Let me just quickly describe it for the people who are not here. I compute xij will be the total number rolled, and then I compute E of x, which is summation S belong to S, P of f xs. And then we are computing 1 by 36 summation S belongs to S of xs. And then we list out all the possible output, and then we add up, and in the end, we get 7. So what is the meaning of this? It means if I am rolling a dice twice, yeah, on average, the expected value would be what? 7. That's the idea.